Good morning students, welcome to iTTV. My name is Teacher Tamindran and today I'll be teaching you Add Maths. The topic of today is Surds. Now the real number system consists of rational numbers and irrational numbers. What are rational numbers? Rational numbers are numbers that can be expressed as a fraction, for example as a over b, where b cannot be 0 because in any fraction the denominator cannot be 0. Now an irrational number cannot be expressed in the form of a fraction as a over b. For any fraction the denominator cannot be 0. Now surds are irrational numbers. They are exact values that cannot be expressed as recurring decimals. In real life, the surds were used to build ancient bridges or pyramids, and that's why the accuracy was so good, because it is not a rounded up value. Now try pressing tangent 60 in your scientific calculator. The value that you would get will be surd 3. Now square root 3 cannot be written as a fraction, and if you convert it to a decimal it will be an irrational number, meaning the decimal place will not stop, it will continue for on and on forever. Now in a right angle triangle that consists of 30, 60 and 90, surds were able to give accurate lengths. Now these two right angle triangles are examples where surds are used in trigonometry. Now if you observe this triangle over here, using a squared plus b squared equals to c squared, we have 1 squared plus with square root 3 squared equals to 2 squared. Now what happens is, when we have a square root and a square, they cancel off each other. So we have 1 plus 3 equals to 2 power 2, which is 4. Now another example would be the right angle triangle over here. Again, by using Pythagoras, we have 1 squared plus with 1 squared equals to square root 2 squared. So we have 1 plus 1 equals to 2. Now certain values inside these trigonometric ratios would be surds. Now we have seen previously that both the right angle triangles here obey the Pythagoras theorem, and where the surds come into play is the ratios. So for example, tangent 60 degrees is going to be the opposite, which is square root 3 over the adjacent, which is 1. So we have square root 3 as the answer. And coming to this right angle triangle over here, we have tangent 45 equals to opposite, which is 1, over adjacent, which is 1, which is the answer 1. And we have sine 45 equals to the opposite over the hypotenuse, which is square root 2. Again, this is an expression of a surd. Surds are positive numbers in the form of square root a. If square root a cannot be simplified by eliminating the root, it is a surd. For example, square root 16 equals to 4. Hence square root 16 is not a surd because it can be simplified. On the other hand, surd 3 is a surd since it cannot be simplified or be expressed as a fraction. These are examples of surds and these are not surds. For example, if you were to press square root 2 in your calculator, you would get this value, 1.41421, and the dots at the back meaning that the decimal place would never end. So it cannot be expressed as a fraction or a rational number. Square root 5 is another example of a surd. If you were to press calculator, you get 2.23606 and so on. And another example would be the square root of 7, which also you would observe that the decimal place doesn't stop. Now these are not surds because they can be simplified. Square root 25 is just 5, square root 4 over 9 is 2 over 3, and square root 36 is just 6. Now we got to take note over here that square root of 4 over 9 can be first expressed as square root 4 divided by square root 9, and that is how we get 2 over 3. Next, you're going to learn how to change recurring decimals to fractions. For example, 1 over 3 can be expressed as a recurring decimal as 0.3333 and so on. What are the steps required to change from this recurring decimal to the fraction? So the steps to convert the recurring decimal 0.33333 to 1 over 3 would be first by letting the recurring decimal as a unknown, let's say k, and then we want to multiply this to get rid of the decimal. So we choose 10 times with 0.33333 so that the decimal moves one place, and now we are at 3.33333 recurring. So what happens when we take 10k minus k is that we see the recurring part at the back here is repeated. So when we subtract, all the 3's at the back here gets cancelled off and ends up giving us just number 3. So in other words, we are left with 9k equals to 3, giving us k equals to 1 over 3. And that is how we obtain the answer of 0.33333 equals to 1 over 3. The following example would be to convert 1.272727 to fractions. So we're going to tackle this question by first let 1.272727 recurring equals to a plus some number n. Now the a would represent the number 1 over here. So this can be rewritten as 1 plus with 0.272727 recurring. Hence, we have n equals to 0.272727 recurring, and I want to get the first round number from the recurring decimal over here. So I need to multiply this by 100. That would move this 2 times, giving us 27.272727 recurring. If we would take now 100n minus n, we would obtain 27. So we have over here 99n equals to 27. We have over here n equals to 27 over 99. And once we have obtained the value of n over here, we take the value of n and we substitute back into our first expression a plus n. So we have a plus n equals to 1 plus with 27 over 99, and this giving us 14 over 11. The next part would be the relationship between surds and indices, and the 3 formulas below shows you the relationship. Square root of x equals to x to the power of half, and root n of x equals to x to the power of 1 over n, and the third one giving us x to the power of m root of n equals to x m over n. Before we go to the next part, we need to understand these 2 properties of surds. For multiplication within a surd, it can split individually to two different parts. The same applies for division. Surd of A over B can be rewritten as surd A divided by surd B. And these are common mistakes. The same rule does not apply for addition and subtraction. In other words, surd A plus B is not equals to surd A plus surd B. And surd A minus B cannot equals to A minus B. So this symbol has to be used. So the first example we have over here would be to simplify square root 3 times the square root of 5, or surd 3 times surd 5. In other words, we're going to use from this step to bring it back to this step. So you can see surd 3 times surd 5 can be rewritten as surd 3 times 5. Your A is 3, your B is 5. And that is how we obtain surd 15 as the answer. Similarly, surd of 20, we could split it up as surd 20 equals to surd 4 times surd 5 using this rule, and surd 4 equals to 2, and surd 5 cannot be simplified, it's an irrational number, so we have 2 surd 5. And lastly, we have, using the division rule over here, that surd 20 divided by surd 5 can be rewritten into this form as 20 over 5, giving us surd 4 that simplifies to become 2. Let's look on an example of how to simplify surd 12 plus surd 20. So surd 12 can be expressed as the square root of 4 times 3, and surd 20 can be rewritten as 4 times 5. Now, according to the earlier example, we know that multiplications can split. So I'm going to rewrite this as surd 4 times surd 3 plus with surd 4 times with surd 5. And surd 4 can be simplified. So this gives us 2 times surd 3, and this gives us 2 times surd 5. So finally the answer can be rewritten as 2 surd 3 plus with 2 surd 5. The next example would be to simplify surd 12 plus surd 50 minus surd 18. Now surd 12 can be expressed as surd of 4 times 3. Surd 50 can be expressed as surd of 25 times 2 minus surd 18 can be expressed as surd of 9 times 2. As the previous example, we're going to split it further. Surd 4 times surd 3 plus with surd 25 times surd 2 minus surd 9 times surd 2. And this can be simplified as 2 surd 3 plus with 5 surd 2 minus with 3 surd 2. It's important to observe over here that these two can simplify further because they have a common surd 2 over here. So this can be rewritten as 2 surd 3 plus with, taking out the common term surd 2, we have 5 minus 3 in brackets. So finally we have 2 surd 3 plus with 5 minus 3 gives us 2 with a surd 2 over here. I'm going to explain further on how these two can be combined, because it's quite usual for students to confuse this part. Now taking this further up over here, we have 5 surd 2 minus 3 surd 2. Now the surd 2 can be expressed as just a variable. So I could say let x equals to surd 2. Hence, we have 5, surd 2 becomes x, minus 3, and again surd 2 becomes x. So we have 5x minus 3x giving us 2x, and this would be 2 square root 2, since x equals to square root 2 over here. The next part of the lesson would be involving how to rationalize the denominators for surds. Now if you look at the first expression, we have surd and a conjugate surd. If we have m square root of a, the conjugate of it is also the m square root of a. And look at number 2. We have m surd a plus n surd b. The conjugate would be by reversing the sign of the part n. So the conjugate surd would be m surd a minus n surd b. And the third example, we have m surd a minus n surd b. So the conjugate, we need to reverse the sign of the back part, the n, which will give us m surd a plus n surd b. So before we move on to the next example, we need to take note of this property. Surd a times surd a equals to a. Why? Now, from the laws of indices, we have already known this, that am times an equals to am plus n. Hence, surd a times surd a can be rewritten as a to the power of half plus with a to the power of half, giving us over here a to the power of half plus half, which is a to the power of 1, and that is just a. Okay. The next example would be to rationalize this expression here, 1 over surd 2 minus 1. So the first step would be to multiply the numerator and denominator by the conjugate. If the surd is square root 2 minus 1, the conjugate is going to be square root 2 plus 1. So multiplying out as usual fractions, we have 1 multiplied square root 2 plus 1 giving us square root 2 plus 1 over square root 2 minus 1 multiplied by square root 2 plus 1. So earlier we have established that square root a times square root a is going to give us a. Hence, by expansion of the bracket, we have square root 2 times square root 2 gives us 2. Square root 2 times positive 1 gives us positive square root 2. Minus 1 times surd 2 would give us minus surd 2. And finally, minus 1 times positive 1, which is negative 1. So we have square root 2 plus 1 divided by surd 2 minus surd 2 cancel off each other. So this part would be 0. 2 minus 1 is 1. Hence the final answer is surd 2 plus 1. Now another way to look at this expression would be using the identity of the algebraic expansion. A minus b into a plus b would give us a squared minus b squared. Hence, by applying that over here, we have square root 2 to the power of 2 minus 1 to the power of 2. So this gives us 2 minus 1, which is equals to 1, which is the denominator over here. Okay students, the next example would be to rationalize this expression. Surd 3 minus surd 2 divided by surd 3 plus surd 2. Now the key to this question is to first identify what is the conjugate. Since the denominator is surd 3 plus surd 2, the conjugate would be surd 3 minus surd 2. So we got to multiply the numerator and denominator by the conjugate of the denominator. So here the conjugate is surd 3 minus surd 2, and again we have surd 3 minus surd 2 over here. Now expanding like two quadratic brackets would give us surd 3 into surd 3 gives us 3. Surd 3 times surd 2 would give us minus surd 6. Surd 2 into surd 3 will give us another minus surd 6, and minus surd 2 times surd 2 will give us a plus 2, divided by, again by applying a squared minus b squared, because this is a plus b, a minus b, we have surd 3 squared minus with surd 2 squared. So simplifying the numerator gives us 3 plus 2, which is 5, minus 1 surd 6 minus 1 surd 6 gives us minus 2 surd 6. Square and a square root would cancel off each other, giving us a 3, minus, again square and a square root would cancel off, giving us a 2. So final answer would be 5 minus 2 surd 6. The next example would be a challenge question. How to solve an equation involving surds in this form? The first step would be to square both sides of the equation. And we have to next expand this like a quadratic equation, meaning we have two repeated brackets side by side. So upon expansion, these two are exactly the same surds. Recall earlier on what we did. Surd A times surd A gave us just A. Same in this case, surd 2x plus 2 multiply with surd 2x plus 2 would just give us 2x plus 2. When these two surds multiply out each other, they are not the same. So we just got to write them individually. So this will be written as 2x plus 2, 2x minus 1. These two surds are not the same. So we just got to write them out. And finally, these two are the same. Applying surd A times surd A is A. We have over here surd 2x minus 1 times surd 2x minus 1 would be just plus with 2x minus 1 equals to 9. And these two are exactly the same. So one of this plus one of this will give us two of this. So we have 2 surd 2x plus 2 surd 2x minus 1, and we got to add up all the variables over here. 2x plus 2x gives us a 4x, and 2 minus 1 gives us a plus 1 equals to 9. So we have 2 surd 2x plus 2 2x minus 1 Bringing it over to the other side, we have got 8 minus 4x. And continuing from this step, we have 2 third 2x plus 2 into third 2x minus 1 equals to 8 minus 4x. What we could observe is there's a multiple of 2 on the left hand side, and all the numbers on the right hand side also have a multiple of 2. So I'm going to divide the left by 2, and I'm going to divide the right hand side by 2 over here. So we can cancel off the 2. 8 divided by 2 gives us 4, minus 4 divided by 2 gives us 2x. So we are left with this expression now, third 2x plus 2 into 2x minus 1 equals to 4 minus 2x. And here we need to repeat the step of squaring both sides again. So the square roots and the square would cancel off. So we are left with 2x plus 2, 2x minus 1 equals to 4 minus 2x into 4 minus 2x. So upon expanding this side of the equation, we have 4x squared minus 2x plus 4x minus 2 equals to 16 minus with 8x minus 8x plus 4x squared. Now we see a 4x squared on the left and we see a 4x squared on the right. We could cancel off. I'm going to bring all the x variables to one side of the equation and all the numbers to another side of the equation. So first step, we simplify these two. We have 2x minus 2 equals to 16 minus 16x. So we have 2x plus 16x equals to 16 plus 2. 2x plus 16x giving us 18x equals to 18. Finally, we have x equals to 1. And we have obtained the solution as x equals to 1 for this equation. So let's test our answer. Take x equals to 1, put it in here, and put it in here. So we have square root of 2 times 1 plus 2 plus with square root of 2 times 1 minus 1. So this gives us 2 plus 2, and this gives us 2 minus 1. So we have square root of 4 plus with square root of 1. Now the square root of 4 is 2. The square root of 1 has to be 1. And 2 plus 1 equals to our answer over here, 3. And to challenge yourself further at home, you could try out this problem. Third x plus 2 plus third 3x minus 2 equals to 4. And the answer to this question would be x equals to 2. So students, to wrap up the lesson today, which we have studied about surds. Surds are irrational numbers that cannot be expressed as fractions. We have seen some usages of surds in a right angle triangle and its connection with Pythagoras theorem. We also have seen how to simplify expressions using surds, some properties, and also how to solve equations involving surds. I hope that this lesson has enabled you all to understand further calculations involving surds, and thank you for watching iTTV.